Okay, I know there are a lot of terms and conditions, so let's just break it down with a real-world scenario. Although the standard for A and B class networks specify 8 and 16-bit masks respectively, it's common to assign non-standard masks for subnets, resulting in much more limited address spaces. Right? For example, using 10.xx.yy.0/24 results in 256 host company subnets, right? So this is done for scalability and, of course, security. Okay, so we're the system administrators in Company X and ready to build. We have decided to use 192.168.x.x as the private IP address space for our company. If we use the natural mask 255.255.0.0, that means we use the first 16 bits for network ID, and we'll have a single network. So in this case, we can address 65,536 devices in this network. Of course, the first IP and the last IP we're not allowed to use, so the number of IP addresses actually 65,536 minus 2, you do the math, but in practice, for ease of use, it's pretty much used as the power of 2. So you can use an IP address in this network from 192.168.0.1 to 192.168.255.254. But we need to have different networks, one for the managers, one for the developers, one for the servers, etc. So, for the sake of our use and our sanity, let's use the next 8 bits for subnets. In this case, we have a subnet mask of 255.255.255.0, 8 bits for subnets, and 24 bits for the network ID in total, 8 bits left for addressing the devices under the subnets. So as a result, we can create 256 subnets and address 256 devices for each one. Now we have 256 address ranges for 256 subnetworks. So the table here shows a few examples of our potential subnetworks. The red colored blocks are added to the network ID as subnet identifiers. The rest of the 8 bits are used as the host IDs. In the 4-block decimal notation, the third block identifies the subnetwork and the last block identifies the host. So, breaking it down, it's much simpler now, isn't it? Excellent. Let's move on.